Okay, today we have Keller from Notre Dame, and he will speak about the polynomial functor in arbitrary characteristic.
So thank you for those that showed up. Unfortunately, the ones that don't go to the first talk will have no idea what the second talk is about, probably. But for this one, let's start it really low. So I want to kind of start by a leading example, which is talking about exterior powers. And in particular, let's just think of the second exterior power as a functor. So what this does is if you're handing a matrix, and in particular, I'll take like a 2x2 matrix. So you may know already that if this is my matrix M, then when I take the second exterior power of M, then this should be a map. If I do a matrix of a map.
Sorry, you have to wear the microphone.
The microphone and
Yeah, here, yeah, 2 and 3, right?
Yeah.
Yeah, I know.
I don't know how to this. Okay. Probably that's curable. Okay. So right, if we want, you can view a matrix as really a map between vector spaces, in this case, 2 vector spaces of rank 2. And so if this is a functor, then this should be a map that goes from the second exterior power of K. Let's say that K is a field. Oh yeah, K is always going to be algebraically closed throughout the talk, just to make some things easier. So this is a map that should go between these two things, but both of these are one-dimensional, right? If I take the second exterior power of something 2-dimensional, I just get 1-dimensional. And so what is it more concretely? Well, it's literally multiplication by the determinant of this matrix times A2, 1. And in general, even if you have a bigger matrix, if I take the second exterior power of something that's bigger, say, I'll say phi is some map between 2 vector spaces over here, then the second exterior power should be something that goes from wedge 2v to wedge 2w. And if you look at its matrix representation, what does it look like? It looks like it's a new matrix where the entries are coming from 2x2 subdeterminants of the original matrix phi. So concretely, after choosing basis, you're going to get 2x2 subdeterminants of the matrix phi. And this is an important point. And this is kind of leading you into the idea of a polynomial functor, because if you're familiar with determinants, then a determinant is a degree, in this case, is going to be degree 2 if it's a 2x2 determinant, and it's homogeneous, right? And so when I apply this functor to a matrix, I'm getting a new matrix, but the entries of that matrix depend on the original one in a polynomial fashion. And this is precisely what it means to be a polynomial functor, right? And so definition, and I'm going to put in parentheses here a strict, but you can ignore this. Just ignore this. Just in case some people were already experts, I should put this to be technically correct. So a strict polynomial functor, or just a polynomial functor. So it's a functor on the category of vector spaces. So it goes from vector spaces over K to back to vector spaces over K. And it satisfies the same property that I said before, such that if you hand me any map, phi goes to V, go from V to W, then I can view this as a matrix with some entries. So if then, when I apply the functor to phi, this is going to be a map between 2 more vector spaces, P of V and P of W. And if I look at the matrix representing this, then the entries should be polynomials that entirely depended on the entries of this original map phi, right? So it is represented by a matrix with, oh wait, I can move this. Nice. With polynomial entries. All right, only depending on phi. Okay, so the canonical examples that you may have seen before, well, I already gave at least one, but 2 is not special in that regard over there. So the 2 most standard examples are the dth exterior power functor in general. So when I take the dth exterior power, again, you have a similar description of the terms of the matrix. They're coming from d by d subdeterminants of the original object. Those are all degree d, and they're homogeneous. So this is a polynomial functor of degree d. The degree is the thing that's recording what the entry degrees are here. So this is a degree D polynomial functor. And then the other one that is standard is the dth symmetric power. So maybe just to be precise here, so this is the dth exterior power, and this is the dth symmetric power. Right? And so this is also a degree D polynomial functor. Okay, the entries are a little bit more annoying to describe, but they are similarly homogeneous degree D polynomials when you kind of run through the basis choice here. Okay. But the most special thing about these is there's much more than this. This is not everything, of course, for a chosen D. And this is kind of the first thing I want to get into. So there's a distinguished class. Also, stop me for questions whenever. This is, after all, a learning seminar. I already know this, so if you don't, then it'd be good to ask. So there's a distinguished class of polynomial functors. And they're called Schur functors. Well, I'll put a comma here. So called Schur functors. All right. And that's kind of what I wanted to take the time to at least define in a nice way today and in a very concrete way. Is there really only one good piece of white chalk? Oh, is there a box? Oh, right in front of me. No. I said good chalk. It's good enough. Okay. So let's see. So I want to talk about Schur functors. Maybe some of you have seen this before. Maybe some of you haven't. Maybe some of you know kind of a different way to define these things. If you're more representation theoretic, you might say, oh, these are your highest weight representations that are irreducible, but that's only in characteristic 0. And you can define these actually in arbitrary characteristic using a very nice construction from the 80s. But in order to talk about this, I first need to tell you what a partition is. So, and also kind of the notion of a Young diagram. So a partition is a non-increasing tuple of integers so I typically, the standard notation is to use a lambda. So lambda is equal to lambda 1. That should be greater than or equal to lambda 2, lambda 3, and so on and so forth. All right. And to any partition, you can associate to a Young diagram. So partition lambda. What you can do is you can write a left justified array where the row lengths are just coming from the entries of the partition lambda, right? So we can write the following. So I'll just write it kind of diagrammatically first. So this is your first row. Yeah, what's up?
So when you call it a partition, are you thinking that these things are non-negative, or could they be negative?
So they can be negative, but actually, for the purposes of this talk, those weights will be rational representations. So actually, let's assume that these are all non-negative as well, just to avoid me saying something that would actually be wrong for fresh.
If you have a 0, does it mean 0 all the way up?
Yeah. You can think of these as infinite tuples if you prefer, by just padding it with as many zeros as you need. Yeah. Other questions? Okay. So the next one is a lambda 2, and so on and so forth. So just as a concrete example, 3, 3, 1, which again you could view as padded with infinitely many zeros if you want. This corresponds to the Young diagram given by 3, 3, 1. All right. So this is just a nice way to repackage this, and actually it's going to be very significant in the context of Schur functors. But also, given any partition, this reinterpretation is useful because there's kind of there's an obvious involution that you can do to this, which reflects this picture along the main diagonal. And since I'm reflecting the shape and the size of the partition just comes from counting the number of boxes, this gives me a new partition, right, of the same integer, but it's going to be different. And so I'm basically just reading off the column length instead. So given a partition, and we call this the transpose partition. So which I'll just do lambda transpose by reading off the column lengths of the Young diagram. of the Young diagram. Close enough. Okay, so just doing it for this example, the transpose of this, while I look at the picture, the row lengths are giving me the original partition. I'll instead read off the column lengths, and so I get the partition 3, 3, 2. So this tells us that 3, 3, 1 transpose is 3, 3, 2. 3, 2, 2, sorry. I knew that. Good. Okay. And I already stated this before, but because of the fact that this comes from kind of reflecting across the main diagonal, if I do it twice, I get back the original thing. All right, so lambda transpose transpose is just lambda. Okay. All right, so let's define a Schur functor. It turns out, well, the definition is not that bad. It's just that kind of getting your hands on these things explicitly is the thing that's a little bit more painful. The definition I'm using here is kind of the original one put forth by Keen, Buchsbaum, and Weyman in 1982. All right. And so this definition actually is completely independent of the base ring itself. I don't even need to assume I'm working over a field to define this. These are amazingly well-defined functors. They're universally free, which means they commute with any base change. They're great. This is why I call them a distinguished class of functors in this category. And so how are they defined? Well, I'll need two pieces of notation. They're parameterized by a partition. I'm going to use two pieces of notation for this. So the first one is if I write the following. So this is like the exterior power. And what this means is it's a shorthand for I want the tensor product of exterior powers given by where each exterior power is parameterized by just reading down the columns. So I'll write a quick example just using that right after this. So lambda m transpose say, where this means the first entry of lambda transpose, second entry, so on and so forth. But literally, this is just saying read off the column lengths in order. So as I said, so if I did wedge of columns of 3, 3, 1, as in this example here, then this is the same thing as just do third exterior power, tensor second. All right? And then likewise, I'll use a similar notation for symmetric powers. If I write S to the rows of lambda, it's the exact same thing. It's just now I just actually use the entries of lambda, not the transpose terms. So this is S lambda 1, tensor S lambda 2, so on and so forth, up to S lambda, say, n. All right? So I'll write it below just to be precise, but if I do it for row 3, 3, 1, then this is just S3 tensor S3 tensor S1. And again, this is my notation for symmetric powers, right? So this is the notation that you need. But once you have this, you can actually define the Schur functor, at least formally. What it should be is, so what it should be is the image of a composition. So the Schur functor. So I'll use this notation as lambda is to be the image of a composition of the following form, where, so basically you should think of the Young diagram as actually giving you instructions to build a module, all right? And what you can do is you can take exterior powers, tensor product of exterior powers parameterized by the column lengths, right? There's always a natural way to anti-symmetrize a whole bunch of tensor products of exterior powers. So this is columns of lambda. So there's a canonical inclusion into just a full tensor power. So this is my notation for tensor power. So T to the lambda of some vector space is just V tensored with itself lambda many times, all right? Yeah.
Write lambda 1 means the first entry of the first.
Yeah. I think I said, but here, yeah, so exactly. So if I write lambda transpose, then I'm thinking of this as having entries lambda 1 transpose, and so on and so forth.
Yeah.
Yeah. Other questions? All right, so this map is a giant anti-symmetrization map. So if you're wondering, just for a little bit more detail, so if you hand me wedge 3, all right, I can look at wedge 3. I can always embed it into a third tensor power, and it's all the tensors that are exactly anti-symmetric with respect to the canonical Sn action, in this case S3 action, that just commutes the tensor factors, all right? So I don't want to do it for 3, but for instance, if you hand me V wedge W, something, and say wedge 2, this should map to V tensor W minus W tensor V under the anti-symmetrization map, right? So if I interchange the order of those tensors, I'll get a negative sign. And that's how you can embed these things in general. And then there's also a canonical surjection onto a tensor product of symmetric powers. And in this case, I'm going to tensor in such a way that it's lining up with the rows of the actual partition. So let me write another, oh wait, I can move this upward. Okay. So a more diagrammatic way to think of this is, well, I'll write the slogan first. So slogan is you co-multiply, because this giant anti-symmetrization map, you can think this as a huge co-multiplication, right? The exterior power has the structure of a Hopf algebra. So in particular, it has a co-multiplication component. You can co-multiply into this giant tensor power. And the instructions that tell you how to do that are given by the columns of the Young diagram. So you co-multiply along the columns. And then if you want to then know how to multiply the things, you're multiplying along the rows. The rows are giving the instructions. Right. So diagrammatically, so if you have wedge column, I want to kind of rewrite this tensor power here in a particular way, because it's actually not completely obvious how to recombine things. This is the step that is a little bit technical and you want to be careful with. So this embeds into the giant tensor power, but if I repackage this information, let's just pretend I plugged in a vector space for sake of making notation easier. So I want to think about, I have a whole bunch of tensors of V, and how many do I have? I have lambda 1 transpose many. And then I'm going to multiply, well, tensor this with another collection of tensors of V. How many do I have? Lambda 2 many. Well, lambda 2 transpose many, and so on and so forth. So there's lambda M. And I'll do some examples right after this, don't worry. But in general, like if you're wondering like, wow, this seems complicated, it's because it is. Like there's just no getting around the fact that this is an inherently technical construction. But anyway, so this is now what I'm saying about the rows give me the instructions for how to recombine these factors. So I've co-multiplied. So the first lambda factor, so this factor right here got embedded into this first tensor component, this one embedded into this one, and so on and so forth. And then the way that I recombine the tensor factors is along the rows. So I do the symmetric algebra multiplication along the rows instead, all right? So I recombine these along the rows, and since in each row, by definition, I have lambda 1 many terms and lambda 2 many, so on and so forth, each of these has a natural surjection. Each tensor component surjects onto S lambda 1, tensor with S lambda 2, and so on and so forth. All right. And so the Schur functor S lambda, yeah. So the first point here is that I forgot to plug in these, but the second point after that is that these operations are at least naturally equivariant. So the Schur functor, I'll talk about this a little bit more, but polynomial functors are equivalent to asking about polynomial representations of the general linear group. And so any kind of construction that you would kind of use to build these things should be functorial in construction. And it should also, once I plug in a vector space, these should all be equivariant in nature, right? So all of these maps are equivariant. Now, in terms of the intuition for why you would choose this definition, this is actually, there's no lowbrow way to say this, basically. There's a few different perspectives. One way is there's something called a Borel-Schur algebra. And this is kind of there's a way to present these things over this Borel-Schur algebra, and it turns out that that co-kernel is exactly the things that are in the kernel of this map. So you kind of get, I can't give you a good answer to this question. There's some highbrow answers, but there's not really like an intuitive like, ah, yes, of course, this is the definition. I think that they looked at these for a long time and just kind of deduced that this was the correct thing, and it worked exactly how they intended it to. So the short answer is no. I don't really know if there's like a good intuitive reason for why you would do this. At least not one that is just following from elementary principles.
What are the goals? What we intend? They did exactly what they wanted.
The goals is, so the goal is that you construct a representation. So S lambda V, so this has an action by the general linear group. Just by construction, if you define it as an image of a composition of equivariant maps, it has an action by GLV. And then also, this means that you can look at its torus character. So in other words, I'll view it as a K class S lambda V. And by other representation theoretic facts, we knew that these irreducibles should satisfy, say, a Jacobi-Trudy identity. And these things exactly satisfy the Jacobi-Trudy identity, but they're defined over arbitrary base rings. So it's kind of, okay, yeah. But it just depends on whether you consider that elementary or not. But yeah, so these satisfy the Jacobi-Trudy identity. An arbitrary characteristic, right? Other questions? Yeah.
Do you mean that the first one is injected and the second one is rejected separately, or do they form a short exact?
Oh yeah, separately. It's not a short exact sequence. Yeah. Other questions? All right, so let's do some examples. What the? Wow. Oh, wow. Okay, never mind. Not much better. So some examples, I'll start off with some easy examples. So S, kind of the always canonical good first start is S, say, sub 2. Some of you may already know the answer to this, but let's pretend we don't and do it by definition. So the thing that we want to look at to give us the recipe for building this is the Young diagram. So the rows of this, sorry, the columns of 2, well, there's 1 and 1. So what I'm getting here is just wedge 1 tensor wedge 1, right? And then if I look at the symmetric powers, so S to the rows of 2, well, there's only one row and it has length 2. So this is just sim 2. And so if I follow this composition along, in this case, it's kind of simple, and you get an answer that you might have expected if you've seen this before. So if I do wedge 1 tensor wedge 1, and then I embed this into the second tensor power, in this case, this is an isomorphism, right? I'm not doing anything, it turns out. And then the natural surjection here is just the natural multiplication between degree 1 elements to degree 2 elements. So this surjects onto S2. And if I look at the image of this map, well, this is an isomorphism, and the image has to just be this surjection here, or the image of this surjection, which is just sim2, right? So in this case, the Schur functor corresponding to the partition 2 is exactly the same thing as the second symmetric power, all right? So this example is a little bit, feels boring, but it's good to work it out by definition. If you knew the answer beforehand, you might be confused as to how this is recovering that. But this is how. And then likewise, let's just do, for good measure, S sub 1, 1. In this case, the Young diagram that gives us kind of the recipe is this one instead. So, and if I look at then wedge 2, sorry, I spoiled it. If I look at wedge 2, the columns of 1, 1, this is exactly wedge 2. And if I look at instead the rows, then this is just S1 tensor S1. And so we kind of have the reverse situation now. When you want to define the composition, you get the map wedge 2. This embeds inside of T2 by that anti-symmetrization map. I wrote it over there, the green one. It's exactly that map. And then this surjects onto S1 tensor S1, but in this case, it's literally the identity map. You're not doing anything. Oops, S1 tensor S1. So this is just literal equality. And so the image of this inclusion is, well, I just told you it's an inclusion, so it's this original thing here. So S11 is the second exterior power. So is exactly the second exterior power, right? And in general, these are kind of the two, whenever you hand me any integer, there's two canonical partitions that always work. You can always just take, say D is your integer. Then there's two partitions. I can just take, the partition that's just a single part D, or I can do the other naive thing, which is just to think of it as adding 1 to itself D many times, which I'll do with this notation. So if I write 1 to the D, I don't mean raised to the power of D, that's just 1. I mean write it D many times, okay? And in this case, if you just go through the definitions, you find that S sub D, all right, now I have to switch from the, is there another one? Oh, found another one, okay. If you go through the definitions here, SD is the dth symmetric power, and S sub 1 to the D is the dth exterior power. All right. And so Schur functors for general partitions are something that kind of interpolates between these two extremes. On one hand, the trivial partition is, kind of, if you think of this as a trivial functor, this is a trivial functor. And on the other hand, the other trivial partition gives you the other kind of trivial functor. And the things in between are much more complicated to describe in general. Well, you can describe them this way, but if you want more concrete descriptions, it's sometimes harder. So, that one doesn't seem to like to go up all the way. Oh, well, okay. So there's another special class that has a nice description just in terms of a kernel of some maps. And so these are typically called the hooks. So let me define that really quick. So a partition of the form, say A1 to the B. So again, this notation means you have some row has some length A, and all the other row lengths are just 1, and there's B of them, right? So diagrammatically, this is the Young diagram. Looks like A things, and then I've stacked B more things on top of it, right? These are called hooks typically because the shape looks like a hook, I guess. I don't know, whatever. So these are another example that have a really nice description. So if you look at the Schur functor corresponding to any hook partition, then this is the same thing as looking at the kernel of the following map. So one thing I can do if I have a tensor product like this is I can partially anti-symmetrize this tensor. So that means I can embed this inside of SA tensor wedge 1 tensor wedge B minus 1. Right, so this is a partial anti-symmetrization map. And then what I can then do is I can recombine, this is not an injection, this one's a surjection. I can recombine this. I now have just multiplication between these two. Notice that wedge 1 is the same as S1. So I can multiply this onto the symmetric factor. And this gives me a map that goes to SA plus 1 tensor wedge B minus 1. Right? So this is kind of a canonical equivariant description of some kind of object. And what object is it? Well, it turns out these are exactly the hook Schur functors. All right, so this is a nicer description than the one that I originally wrote. And it's not entirely obvious that it's equivalent to the description I wrote, but I'll leave it as an exercise that it's equivalent. Right?
So if you flip it around, you can transpose.
Yeah. Yeah, so if you flip it around, well, you got to be careful. If you flip it around, what you're getting is actually a Weil functor, and you should replace it with divided powers. Yeah, which I'll talk about in a bit. How's time? Oh, good. All right. And so these are Schur functors. Some facts that are useful. Well, not really useful, but more like intriguing, depending on what you find intriguing, are the following. So the first one, just to tie this back to at least one other talk from this semester. And this is in many ways what representation theory, geometric representation theorists would prefer this description. So the first one is that another way to do this is you can take a flag variety on V. There's a canonical class of line bundles on the flag variety, and you can plug in the partition lambda. And if you take cohomology of that, then you're recovering the Schur functor S lambda applied to the vector space V, all right? And in fact, there's no higher cohomology for such line bundles. This is Kempf vanishing. So if you like a geometric description, then this is nice. However, this is not really like a satisfying description. Now, if I were to tell you, okay, now construct it for me for S33, this description is not really going to cut it. It's not obvious how to do it from this line bundle description. The second thing, and this is not going to be a typo, is that S lambda is indecomposable. Indecomposable for all lambda. And let me tell you what indecomposable means. So something is indecomposable if it cannot be written as a direct sum of two proper submodules. Now you may say, is this the same thing as being irreducible? No, it is not. It's equivalent in characteristic 0, but it turns out that in arbitrary characteristic, these things are indecomposable. They are not irreducible. They have proper submodules, and I'll tell you exactly what they are in a second. So be careful with that. So again, indecomposable just means does not decompose as a direct sum of stuff. And it's important that I'm saying direct sum. It does have proper submodules. And then the third thing, just to tie this back to the original discussion, is these are polynomial functors, and the degree is exactly the size of the partition. So S lambda is a degree lambda. By the way, I've been using this notation, but I never defined it. This just means take the sum of the entries of the partition. So this is a degree lambda polynomial functor. Right. Yeah. Yeah, but you basically what you can do is you can view the full. I actually didn't write this. I meant to write this. So there's a category just Pol, which is of all polynomial functors, and this decomposes as a direct sum of the categories of all the homogeneous of degree D polynomial functors. So it behaves the exact same way as polynomials, really, right? Like a polynomial, you can always split it up into a sum of homogeneous pieces. An arbitrary polynomial functor has the same property. I'm about to tell the characteristic 0 story. So in characteristic 0, yes, very nice. We really understand the building blocks and we understand how they relate to each other. In positive characteristic, we do understand the building blocks still, but we have no idea how to piece them together in general. This is a hopelessly open question, in my opinion. But yeah, so just to be precise here, so this notation is notation for the category of degree D polynomial functors, where morphisms are morphisms of functors, i.e. natural transformations. And if I kind of package all of this information together, this whole category Pol actually inherits a monoidal structure. I can take the tensor product of two polynomial functors. And if you think about this in terms of matrices, this takes the Kronecker product. And the entries of the Kronecker product are going to be additive in the degrees of the original entries. So the tensor product functor actually gives you a bifunctor going from Pol D tensor Pol E to polynomial of degree E plus D, D plus E, whatever. All right. So this is also, these behave remarkably like polynomials in this sense as well, where your monoidal structure is kind of like the multiplication between polynomials here. Other questions? Okay. So yeah, let's look at the characteristic 0 story. So in characteristic 0, things are much nicer. So the notion of indecomposability in characteristic 0 is just the same thing as saying it's irreducible. In other words, there are no non-trivial proper submodules if it's in characteristic 0. So S lambda are irreducible functors, right? So this means that there's just no proper submodules, period. And in fact, Paul D is really just the same thing as taking all direct sums of these types of things where lambda has size d. So this is direct sums of S lambda, where the size of lambda is equal to d, right? So in many ways, the characteristic zero story is both interesting and boring. It's still remarkably complicated. This doesn't mean that it's trivial. Yeah. Yeah, I'm gonna write right below this. So yeah, so equivalently, if you ask me to hand you a polynomial functor, P, then all I need to do is just hand you back a direct sum of Schur functors. All right, so P is for any polynomial, so for any P in Paul D, this is the same thing as taking some direct sum of Schur functors where I'm only ranging over some subset of the partitions that have size D. Right, with multiplicities, I can take, the same thing direct summed with itself, right? And it's always going to be a direct sum decomposition. There's nothing else that you can get. They all have to decompose in this way. Okay, that's why I was saying how it's kind of boring, but also very elegant because, well, compared to the positive characteristic theory, you see why this is such a desirable property. So, moreover, the whole point is that this is intimately related, and in fact, equivalent to just looking at representation theory of the general linear group. So there's an equivalence of categories. Good thing I introduced the notation right there. So Paul is equivalent to the category of polynomial representations of what is sometimes noted GL infinity. So what this means is instead of plugging in just a finite dimensional vector space, you can take these functors and imagine plugging in something infinite dimensional instead. Then, right, you kind of have a natural filtered system. GLN sits inside of GLN plus 1. Just think about adding an extra 1 along the diagonal, and so on and so forth. And so the limit of this object is going to be GL infinity. And there's a theory of representations over GL infinity. And it turns out that theory is the same thing as just the theory of polynomial functors. All right, so everything decomposes as a direct sum. And just to be, if you want to restrict the degree, then you have another statement that Paul D is the same thing as just looking at, if you don't like infinite dimensional spaces, which is reasonable, this is the same thing as looking at the degree D polynomial representations of GLV, where you've plugged in any vector space whose dimension is at least the degree of the polynomial functors, right? These are equivalent things. The reason you want the dimension to be sufficiently large is because of the problem of exterior powers. If I plug in something of dimension less than D, then wedge D is 0 on that thing, and you don't want that to happen, basically. Okay. Yeah.
This story about
so yeah, I actually was thinking about this before the talk. I think that you can still write down such an equivalence. It's just that the generators on this side are not so easy to describe. Yeah. So I think that this type of statement, this statement actually is for sure true in arbitrary characteristic, and which I think implies that this is also true in arbitrary characteristic. I've never really thought about it. Okay. So let's talk about what happens if the characteristic is not 0. So if the characteristic is positive, I kind of want to write how you need to modify things. I'm going to start writing in yellow because that's the only good Hagoromo color left. So if the characteristic is greater than 0, then there's some modifications. So instead of asking for direct sum decompositions, this is way too much to ask for in general. You're really only asking for decomposition up to filtration. So this should be replaced with decomposition, as I've just said, up to filtration. And I'll do some examples to tell you a little bit more about what that means. And then likewise, instead of your distinguished class, so Schur functors are still a distinguished class, but they're not your simple subfunctors. They're not really your building blocks anymore. So your S lambdas should instead be replaced by something which is typically denoted L sub lambda. And these are called the simple subfunctors. And I'll tell you why they're called subfunctors in a second, of highest weight lambda. Right. So there's some issues with this, though. These L lambdas are ridiculously hard to understand in general. It's kind of an open question as to how would you, just given a lambda, a partition lambda, how would you describe this in terms of, say, basis elements slash generators or slash, well, yeah. Could you give a similar description for basis elements? For those that are aware, the basis here after you plug in a vector space is parameterized by semi-standard tableau of shape lambda. What is the description over here? Not so obvious. Nobody really knows. Actually, Lusta gave a cool talk on this a few years ago about there is a way to write down a spectral sequence whose E0 page is not technically this, it's a Weil module, and whose E infinity page converges to this. So it's technically a finite algorithm, but who knows how many page maps you have to go before you get convergence. So there are some ways theoretically to write down, this basis, but is it practical? Not so clear. So yeah. But why am I calling these subfunctors? This is also a fact that is very elegant. And it's obvious, or it's well known to representation theorists, but not as well known if you're not a representation theorist. So I had mentioned in my facts that S lambda is indecomposable, right? So this is an indecomposable functor. But that doesn't mean it's irreducible. So there can be a proper submodule that sits inside of it. It turns out there's a unique simple subfunctor that sits inside of here, and it's exactly these simples L lambda, right? So this is the unique of the Schur functor, right? So even though it's not entirely clear, your simples are still parameterized by partitions. And how are these partitions related to the original Schur functors? Well, they always at least sit inside of here, and it's the unique such simple submodule. Another way of saying this is that the socle of this object in the representation theoretic sense is exactly L lambda, okay? And here's an example for how this actually sits inside of here. So let's say that the characteristic is positive, and say that it's just P, some prime P, then we know what the Schur functor S sub P should be. Well, I claimed that we know what this is. This is the same thing as just the Pth symmetric power. And so there should be some simple subfunctor that sits inside of here. And in this case, it's very concrete to work out what it is. Since this is just the symmetric powers, the thing that sits inside of here are the perfect Pth powers. In other words, the Frobenius Fp. So this embeds inside of here. And what's also interesting here is that the co-kernel of this map is what's often called the truncated powers, SP. So it's literally take your symmetric, all your degree P symmetric monomials, and then kill all the ones that are perfect Pth powers. Turns out that's also an irreducible functor. Which one is it? It's LP minus 1, 1. And so what you have here is that this is what I say by, you can only decompose things up to filtration, right? These are two simple objects. So both of these are simple, i.e. irreducible. They fit inside a short exact sequence like this, but this is not a split sequence. There's no way that I could ever decompose this as a direct sum of these two things, right? So this is why I'm saying that you can only do things up to filtration, even though your building blocks are parameterized by the same set. Any questions? Yeah. Oh, I put a hook, sorry. Yeah, I didn't mean to do that. It's a surjective. Yeah. And this is, if you think about, if I kill all the things that are perfect Pth powers, that's exactly modding out by the image here. So this is indeed a short exact sequence.
So if the size of lambda is less than p, is it
Yeah.
exactly the same?
And this is an if and only if. The common way that this is repackaged is that the Weil algebra is a simple, or sorry, the Schur algebra is a semi-simple algebra if and only if the degree is less than the characteristic. As soon as you get to degree equal to the characteristic, you're going to get non-split sequences. So yeah, it's actually an if and only.
So L21 is also bad here.
Yeah, depending on your definition of bad, yeah. There's some simplifying assumptions. So these L lambdas, there's something called the Steinberg tensor product theorem, which tells you that if you want to understand all L lambdas, you only have to understand the ones that are called P restricted. So each part is at most equal to P. And then if you want all the other ones, you just take Frobenius powers of those ones. So for instance, notice that this one is the same thing as doing FP applied to L1. And that's not a coincidence. That always has to happen if it's not P restricted. Okay. How am I on time? Why is there not a clock? 4 minutes? Oh, okay. Ooh, good. What?
The seminar said you answered 3.
Yeah, but like, that's assuming everyone wants to sit through more of this, right? So I don't know. So what was I going to say though related to this? Oh yeah, so the statement, by the way, that this is true, this was proved by Chevrolet in 1951. So this has been well known for a long time that these are kind of the unique simple subfunctors here. So actually, this is a perfect segue though into the second half of the talk. So in the 80s, there was suddenly kind of a shift in perspective. After this paper by Keen, Buxbaum, and Weyman, there was kind of a shift toward a more commutative algebraic approach, because this attempt to understand the polynomial functors in terms of these unique simple subfunctors is a very representation theoretic point of view. But a more natural point of view from a commutative algebraist is to, instead of thinking of trying to under approximate by using a filtration, you can think of over approximating by using resolutions instead. And what object should you use? Well, it turns out, I shouldn't say the projectives, but a distinguished class of projectives. In the category of polynomial functors comes from actually just taking all tensor products of divided power functors. And I'll tell you just a second what divided powers mean. So come from tensor products of divided powers. So just as an aside really quick, so what is the divided power? So if I take the dth divided power of some vector space, the most efficient way to define this is that it's the same thing as taking the symmetric power of the dual and then dualizing that. This operation is sometimes called taking the Kuhn dual of a polynomial functor. And so divided powers are the Kuhn dual of the symmetric power functors, right? So it turns out that these things are kind of our projective building blocks. And you can ask, and in fact, it's a theorem that follows from some relatively standard theory about polynomial functors. An equivalent characterization of a polynomial functor, and I'll write this as a theorem and then maybe say some more. So this follows from work of James Green, I guess, from 1980, but also was really pushed by Keen and Buxbaum in a sequence of papers starting around 1988, which is that a polynomial functor is equivalently any functor that admits a resolution by tensor products of divided powers. So I have to write all those words. Admitting a res by tensor products of divided. All right, and so you can ask, and this is the question that Buxbaum asked, instead of looking at Schur functors, don't worry, I'm about to end. This Kuhn dual operation, I can do this actually for any Schur functor. And the thing that you get is not a Schur functor anymore. It's called a Weil functor. So if I take W sub lambda is going to be my notation for a Weil functor. And how is it defined? It's defined the exact same way. I take a Schur functor, I input the dual, and then I dualize it on the outside. And that is not the same thing as just the Schur functor. And positive characteristic, these are legitimately different constructions, okay? And so the hopeless, well, depending on how hopeless you are, open question is what is the minimal resolution of a Weil functor? So I'll just write W lambda by tensor products of divided powers. I'm just going to write tensor products of divided powers. Tensor products of divided powers. Okay, I just can't be asked to write that again. This is an open question. And why did he care? Well, there are a few derived invariants that are particularly important. In particular, there's something called the Cazul duality functor on the category of polynomial functors, which I'll talk about as kind of the main subject of the next talk. And if you want to compute higher derived invariants of this Cazul duality functor, you need your hands on some projective resolutions. And if you had projective resolutions by divided powers, you can compute these derived functors. And then likewise, if you just take the naive Yoneda definition of extension groups and the category of polynomial functors, that's still well defined. And so these resolutions can be used to define extension groups between Weil functors, W lambda, W mu, which it turns out it's a theorem of Akeen and Buxbaum. This is the same thing as computing X between S lambda and S mu. Turns out it doesn't matter whether you put in Weil or Schur functors here. So this is the motivation. These are kind of the two questions I'll try to answer in the next part of the talk. So I'll stop here.